So I want to give you another description of classification of torsors. So okay, there's a simple way to do it. The simple way, the standard way is, so let's let F be a locally free sheaf. On X, so X is going to be a scheme. And the usual way is that here we'll take here. So these things, this is the standard way. So in this is the standard picture here. There's another way to do it, and there's actually a correspondence between these. And now here we're going to have, let's say this is a rank R. There's this guy here. Okay, and I'll describe what these things are, but here, this is going to be classes of things that look like matrices over open sets plus, and then we can call this maybe Bij, something like this. Okay, so this is going to be, so this is a matrix, and this is like a vector, and then you compose these here. The thing is that this guy here will have to be compatible. Give the cl f. So this is the cohomology class that classifies the vector bundle, and it lives in GL in X GLR. Okay, let me. Okay, so this is what I want to get at. Is I want to talk about the classification of torsors in here. Okay, that being said, I'm going to go and I'm going to go and say some things. So let F. Let phi from F restricted to UI to OR of UI. So this is so O is going to be O of X, and this I'm just going to omit that. And so these are the trivializations, and then what we can do is we can take the transition maps. These are transitions, and what I wrote down before is that here, this is going to be, so this is the cocycle that classifies F. Okay, so we have this construction here. And so what I want to say is that if okay, if eta ij is in H1, or let's say, let's do it like this. Eta ij, the class of eta ij is in H1, and they'll say with some cover U of F, then the following, we'll get the following correspondence. Phi of eta ij is equal to bij. And so this bij is this thing here. So this part here, this comes from these eta ij's by plus the transitions. And this thing here, so not literally plus, but, and this thing here is the class, the transition maps for the vector bundle, and this thing here is the kind of the part of that comes from these eta ij's. So this is my claim, is that this thing here relates the two concepts. First, let's recall some things about the affine linear group, so that we just have some footing. So, facts about the affine linear group. And this is kind of more generally about semi-direct products, but this is the group which is a semi-direct product, where you have GA to the R, and it goes like this on GLR. So this is here. This is a normal subgroup, so this is pointing, the arrow is pointing like it's a normal subgroup, and here we have this thing acting on here. On the left, there's a left action here on the additive group. This is by matrix multiplication. Okay, and let me just kind of describe. So that's the two different group laws here. So on this side, I'm going to write what this thing looks like, and then here I'm gonna write things about the affine linear group. So here we view these as AX plus B's. Okay. So this is a matrix, and then this is a vector. Okay. And then over here we're going to write them as A B's. So let's see, write it as B A. Okay. Here we're going to have composition A1x plus B1 composed with A2x plus B2. So this is equal to, well, this is equal to A1, and then we plug this whole thing in, 2x plus B2 plus B1. And so this is equal to A1, A2, x plus A1, B2 plus B1. Okay, so I just distributed this whole thing, and this is what the group law looks like. Here, we're just going to do the thing that we do for semi-direct products, is that, okay, so I write it like this, and here we, let's see. Oh yeah, the A acts on the left of the B's, okay? So this is why we read it like this, and then the multiplication is that we do the multiplication here, and in this case the group law here is abelian, so we write it additively, and then we multiply this one through, so it acts and then adds. So this is equal to B1 plus A1 B2, and then this is A1 A2. Okay, so these matrices just multiply like here. And here we just get B1 plus A1 B2. So these two groups are isomorphic. Okay, so these are the two things that we have. What I'm about to say holds pretty generally for semi-direct products. This rule. Okay, so let's go back to here. This thing is what we wanted to investigate. Let me just write out what a cocycle condition looks like for a semi-direct product. So the cocycle condition for semi-direct products. Okay, so what we do is we just write it out: Bij, Aij, Bjk, Ajk, Bki, Aki. Okay, and what happens here when we write this out? Well, this thing is Bij plus, and then we multiply A1j, Bjk, and then we multiply these two, Aij, Ajk, this is an I, and then Bki, Aki, and now we do it again. So here we now multiply this thing times this and add it to this. Bij plus Aij Bjk plus Aij Ajk Bki. And now we just multiply these all together. So Aij Ajk Aki. If this whole thing is equal to 1, that's the cocycle condition, that things like this add to 1, then this tells us the following. 1 in this group is really 0, 1. It tells us two things, that Bij, oh, where do we go? Plus Aij bjk plus Aj ajk. I'm just copying the whole thing down. This is 0, and then Aij ajk aki is equal to 1, or the identity. Okay, so this is kind of a twisted cocycle condition, and this is what we're going to use to show how cocycles of the so again, what were we saying? We're saying cocycles here are related to cocycles here. The formula we gave was this thing, and now I'm going to prove it. Okay, so we had this, and this is what I want to recognize eventually. So to recognize this, what do? Well, we're just going to take this expression again. So the expression, let me write it down. Well, we could do phi eta ij is equal to this bij here. And so this is a vector. This is eta ij is this cocycle in check cohomology for f. Okay, and so since it's a cocycle for f, so this is the formula that we want to check. We have this condition. Eta ij plus eta jk plus eta ki. Okay, so this is 0. And now we can apply phi to all of these. Phi eta ij. And so this is a homomorphism, so phi. So I just apply phi to this whole thing. And this is technically on the triple overlap. We don't need to worry about this too much. And now we can kind of adjust this a little bit. Plus, okay, now what we'll do is we'll do phi, and then we'll add something in. Those two things cancel. Okay, and then we'll do the same thing again, phi, and then we'll do phi j inverse phi j, phi k inverse phi k, and then we'll do eta ki. And this is still equal to 0. Okay, so now we can clump. Okay, so if we let, so we'll take this as a definition. This thing here is bij. Okay, now we have this thing, this is bjk, and now we have this transition matrix. So this is aij bjk from here and here. Now we have two matrices, and now we have bki. So this is aij, aj. Oh, what did I call this? I did superscripts. Ij. Sorry, ij, and then we had jk, and then we had b ki. Okay, and so this thing here is now the twisted cocycle condition. So this is the thing that we wrote down here once we had these matrices. I guess I did it with subscripts, and now I'm doing it with superscripts. That doesn't matter too much. So in the next video, I'm going to show how to make this procedure going from, let's see where to go. Well, the thing from torsors to, for the different H1s, the H1 of the affine linear group to the H1 of the locally free sheaf, well defined.